So good morning or good afternoon, whatever time you're listening to this. So today's presentation is about how do we reconstruct or rehabilitate a pavement once we know what the pavement structure is, and once we know what the design traffic is, and once we have some sort of falling weight deflectometer data. So the options we're going to go through in this presentation are granular overlays, asphalt overlays when and where they're possible, in situ stabilization methodologies, but also what sort of data we actually need to carry out the overlay design. So we'll move on to the next slide. So the data that we've been provided based on the visual assessment that has been carried out is that there's a lot of crocodile cracking. So generally, different forms of cracking, there's different reasons for it. So for crocodile cracking, that represents that the pavement is weak. So why is the pavement weak? Is there moisture that's gotten into the pavement layers, the granular layers, or is there moisture that's gotten into the subgrade? Sometimes it's moisture, that gets in, it weakens the pavement. Sometimes it's just excessive loads. So you could just have heavier traffic that the initial pavement wasn't designed for. So that could lead to significant rutting of the subgrade, but it could also just lead to asphalt fatigue. So you get a lot of stresses induced in the asphalt, causing tensile strains at the bottom, which leads to fatigue of the asphalt. This, if you do deflectometer testing, this is often represented with very high curvature values. As we'll continue with this presentation, we'll see that where that happens and where that doesn't happen. Obviously, excessive loads are excessive if the pavement is inadequately thick. So if the pavement is very thick, then it's sometimes designed to handle larger loads, and you shouldn't get that subgrade rutting. You may still get the asphalt fatigue, but you shouldn't get the subgrade rutting. But yeah, the biggest concern with most pavements is usually moisture getting into the pavement, and that's what we want to do. We want to stop moisture from getting into the pavement, and when it does get in, we want to have subsoil drains where the moisture can drain out. So the crossfall of the pavement at the surface, but also the constructed pavement itself must be good so that the moisture drains away. One of the issues that can happen is actually improper compaction. So we take care of compaction during construction. There's obviously specifications, there's quality assurance, but from time to time, we can miss soft spots. We shouldn't, but we do. And the aim is to identify soft spots and make sure that compaction is carried out, and there's usually, scale A, scale B, scale C testing in Vic roads. But you want to carry out and you want to ensure that the material is constructed as specified. And if it has been, then there shouldn't be issues, but we find out that a lot of times it isn't. But you don't want to have poor compaction be the reason why your pavement failed, and ideally you never want to have a failed pavement within that design life, but if it does happen, then you need to find out what the reasons are. But crocodile cracking, those are the reasons. Excessive loading, moisture in the formation, subgrade rutting, just weakened pavement layers, and sometimes poor compaction during construction. So some of those we've already spoken about. The other reason, one of the other things that's been noticed on this pavement is pumping of fines. So you get pumping of fines when water gets into the pavement. Those fines in the crushed rock can start coming to the surface. So it's more a result of what's happened prior to it. The pavement's cracked up, water's now getting into the pavement, the fines are now coming up to the surface, they're getting pumped up to the surface. So the next slide is about what the constructed pavement is. The constructed pavement is a 40 mil dense graded asphalt surface with a 125 mil granular base course, 125 mil upper sub base, 125 mil of lower sub base, which is a class 2 crushed rock, 40 mil aggregate, and a silty sand subgrade CBR 5%. Just going back so continuing on, so now that we've got what our potential causes of cracking are and what our constructed pavement is, we should probably work out what was the previous design life or the approximate design life of the constructed pavement when it was built. So just going into Ostrode's part 2, figure 8.4, we can see that depending on what methodology you use, if you include the thickness of the asphalt in the overall thickness, or if you choose not to. If you choose to include the asphalt thickness in the overall pavement thickness, then you've probably got a pavement that could withstand 3 by 10 to the 6 ESA. You just work horizontally across the thickness of granular material, and you work up from the CBR line, and you get 3 by 10 to the 6. Alternatively, you could not include the thickness of the asphalt, and in which case you've got roughly 7 by 10 to the 5 ESA. So then it's roughly a 375 mil thick pavement, CBR 5. So you go to so depending on what methodology was used at the time, you're anywhere between that 7 by 10 to the 5 to 3 by 10 to the 6 ESA. So we've been provided deflection data for this site. Once we've been provided that deflection data, we need to carry out some adjustments to the data. So there needs to be temperature corrections, seasonal variation corrections. Have we been given deflectograph data, FWD data, Benkelman beam data? But also, if we have been given FWD data, what was the pressure per drop? Was it 40 kilonewtons? Was it 80 kilonewtons? Was it 120 kilonewtons? So we need to carry out several corrections to the data that we've been given. In this case, the data that was given to us had 40 mil asphalt, and it had been carried out at the temperature that was the weighted mean average temperature for that area. So so the seasonal variation, the seasonal correction was 1, the temperature correction was 1, and there was no correction to be made to the load because we'd done the testing at 40 kilonewtons. So once we've got that data, we've made the corrections, the next thing we want to do is plot that data on a chart. Generally speaking, D naught versus chainage. Plotting it on a chart, rather than just looking at it numerically, gives us an idea of, where the lots or the, where we should be chunking one set of data as one set and another set of data as another lot, a third lot, a fourth lot, and so on. So putting things on a chart obviously just makes things easier to visualize. So in this case, what we've got, we've plotted the data, D naught versus chainage on a chart. We've had a look at the plotted data, and we can see very clearly that there's a lot down the bottom, roughly from chainage 0 to chainage 420, and then there's a lot up the top, which is from chainage 440 onwards to the end of the road. So we can see that these two lots, the road is performing quite differently at these 2 points. The road deflections are quite low at one point, the road deflections are quite high at another point. Now, there could be multiple reasons for that. Sometimes load deflections correlate to a pavement that is either performing really well, but it could also relate to a pavement that actually has been constructed with a completely different methodology. So in this case, given that we've been given a constructed pavement profile, we will assume that the pavement is performing or recording low deflections because it's actually performing well. In other words, it's in good condition. While we've seen cracking at the surface, the deflections will indicate otherwise, that maybe the cracking at the surface is more indicative of asphalt fatigue rather than actually subgrade rutting, because the deflections are quite low, so to speak. Whereas on the other end, moving from chainage 440 onwards, what we're seeing is very high deflection. So in that case, you might be getting asphalt fatigue, but then you're also getting that subgrade rutting down the bottom. So you've got you've got this consistently weak pavement throughout. So you've got high deflections, high subgrade rutting potentially, and you've got those low deflections, which while you've got cracking at the surface, indicates you've got asphalt fatigue happening, but you might not be getting that subgrade rutting down the bottom. And they might require different forms of treatment depending on what you how you could treat those areas. So just in terms of the data that we've got this time around is just sort of D naught. So we've just got D naught values with the chainage. Ideally, we'd want to get a lot more data, and this is a slide of typically the output that you get from a falling weight deflectometer. So you get your D0, D200, D300, all the way up to D1800. You get your time, the surface temperature, the air temperature, you get your curvature values. So this is typically what we would expect to get from a FWD, tester in terms of data. But in this case, we've just got the D0 values. So there's a bit of missing data that we hoped we should have had, but we haven't got it. It limits us to what we can actually do in terms of overlays. Because we don't have that D200 to D1800, it's very difficult to carry out curvature assessments. It's very difficult to carry out deflection bowl analysis. So there's, the asphalt overlay option is quite limited in this case. We can only really do granular overlay because we can only really design for subgrade rutting because of the D0 value. That's the only value we have. So this slide just talks more about that. It just presents us with, what the curvature function actually is. It's a function of the D0 and D200 values. The D200 means it's 200 mil from the, the center of the plate, but also 200 mil below subgrade sort of thing. And the D0 to D200, ratio or function is very important. It's very important to work out what the asphalt fatigue actually is. That curvature function is important to work out asphalt overlay options. So the design deflection. So we know what our design traffic is. It's 6 by 10 to the 6 CSA. Now that we know what our design traffic is, we can work out what the design deflection is. So this chart comes straight out of Ostroids Part 5. And we can, go work across from, work up from the design deflection and work across where we intersect the line. And we can see that our design deflection should be 0.9. How does that plot with the data that we had? So we can see that, when we plot the 0.9, which is our design deflection, against the two lots that we had, one's clearly above, one's clearly below. So once we worked out what our design deflection is, once we worked out what our lots are, we then, work out, okay, what's the F value to work out the characteristic deflection? Now the F value is the multiplier to the standard deviation. And the F value varies. So it could be, depending on which version of Ostroids you use, whether you use the 2011 version or the 2019 version, it's roughly 1.3 all the way up to 2, depending on the project reliability or the number of vehicles on the road. 2,000, greater than 2,000 vehicles per day per lane, and you're looking at using 2. And if it's less than that, depending on your project reliability, you might use 1.3 or 1.65. But there's also another consideration. How many data points do you actually have? Do you have sufficient number of data points to either use a 1.3 or 1.65 or 2, or should you just be adopting the maximum deflection value in that lot? So in this case, we've got an average of 0.3 for a standard deviation, or very low standard deviation. The coefficient of variation is also quite low. It's less than 13%, which is good. It should be less than 20 to 25% ideally. The maximum D0, 0.45 mils. Low, it's below the design deflection, which is good. The F values, okay, so we've chosen 2 different F values here. While we haven't been given a daily traffic volume per lane, 6 by 10 to the 6 ESA is actually quite high, which would indicate that the daily traffic volumes are greater than 2,000 vehicles a day. Assumption made, but we'll confirm that during construction and detailed design. So, if we were, however, Ostroids Part 5 2019 says you can use 1.33 based on the number of deflections you have. That assumes a 90% project reliability across the board. So depending on whether we use 1.33 or 2, we see that our characteristic deflection is 0.4 or 0.42, which is sufficiently less than that 0.9. It's strong. Subgrade rutting is not a concern, so to speak, based on the data that we've got. Lot 2, however, we've got a very high average, 1.21. Standard deviation and COVAR are quite good. Max D0 is 1.47, which is quite high. And you've got a characteristic deflection of 1.36 to 1.44, which are, above that 0.9. I should say that you should ideally exclude very high or very low points from a lot, as they can lead to biased results. You can treat the very high points in isolation, but the very low points usually indicate the pavement's quite good, and they can just be lumped into the overall lot average. So how do you work out what the granular overlay is? Now this is an extract from Ostroids. It's probably quite wordy, so we'll actually work through an example. So in this case, once we've worked out that, we've got 1.47 as our max deflection, our design traffic is 6 by 10 to the 6 ESA. What we can see is, using this chart from Ostroids Part 5, if we go up from the 1.47, which is our characteristic deflection before overlay, and across to, and intersect that design traffic line of 6 by 10 to the 6 ESA, and then work across, we can work out what the overlay thickness should be, and in this case we can see it's 190 mil for a 1.47 mil characteristic deflection. Now we go back to our table and we look at, okay, when we use a certain F, we get a certain characteristic deflection. 1.33 is Ostroids Part 5 2019. 2 is based on the fact that it's greater than 2,000 vehicles a day, which we're assuming, and it very well might be. And max D naught is because we don't have those 30 points within a data set. So we could choose any of these three, and they might all be considered right. But let's, for this design, be a bit conservative, because it is an arterial road. 6 by 10 to the 6 ESA is getting quite high. So let's go with the max D naught, 1.47 mil. We can see that we need 190 mils of granular overlay. We did have that one very high point, but we've actually designed using that one very high point. So if we adopt the 190 mil across that, chainage 420 onwards, we're solving the concern of subgrade rutting, so to speak, based on Ostroids methodology. For section 0 to chainage 420, so section 1, chainage 0 to chainage 420, you've got very, very low deflections. So you've got cracking, but you've got very low deflections. Resurfacing is recommended. You could seal the cracks so the water doesn't get into the pavement, but at this stage it doesn't seem like any overlay is required. Having said that, let's go to the next slide. So we didn't quite consider asphalt overlays because we don't have curvature data on this road, or given in this data set. If we had curvature data, we could use the curvature charts in Ostroid Part 5 2011 to work out what sort of asphalt overlay we actually did need. You can see the chart there. You can work out what your characteristic curvature is, and then you can go up the line. You would need to, there is a lengthy methodology in Ostroids about how you need to mill out, put back in, reduce and increase deflections, and so on and so forth. I should, however, say that the 2011 version is now outdated. The 2019 version actually does not recommend using the charts anymore. It talks about back analysis and matching deflection bowls. So I've given an example of a deflection bowl, another project that I've recently done using Rubicon software package, where the deflection bowl works out what the back analyzed modulus of a pavement would be at each individual layer, and you're trying to match deflections. So you've got your calculated deflections for the modulus that the software is working out versus the recorded deflections from the FWD testing, and you're trying to match the bowl, the red line to the blue line, reduce the error rate, and then you've got a very good idea of what the modulus might be. So, but you can only do that if you have all the values from D0 to D1800. So you do need all the values, and you need the asphalt thickness, but you also need the total pavement constructed profile. So you need a lot of data in order to carry out the back analysis. So the asphalt overlays are not possible in this instance, but they are possible if more data is received. Although I should probably say that it's an expensive option compared to a granular overlay, and wherever you can do a granular overlay, wherever that's practical and feasible, that's the option you should mostly adopt. Other methods, in situ stabilization could be considered. Typically, the percentage of cement is calculated based on a mixed design methodology, and the gradings that are done on the existing material. So you need to work at the quality and quantity of the existing material. You need to do a mixed design to work out what sort of cement is required to get the strength that you want. There are some charts in Ostroids that can guide you to what sort of thickness you need to get to, or you could do mechanistic analysis using Circly. You input your design traffic and you input your pavement profile. In this case, we talk about importing about 100-150 mil of crushed rock, mixing that asphalt, the imported crushed rock, and the existing base together to form a 300 mil in situ stabilized base sitting on that upper and lower sub base. And then you have like this 300 mil layer sitting on a 250 mil layer, and then you can surface with a spray seal or another 30 to 40 mil asphalt. We've done an analysis and that works in Circly. That's recommended in the report. Hypothetically, or typically speaking, granular overlays are the cheapest option. So in situ stabilization would be considered where you just wanted to reuse what was there. If you had to import any more material, let's just go with granular overlays. Yeah. If you didn't want to import any more stuff, let's look at in situ stabilization. But if you're importing 100 to 200 mil cross rock, then you might as well just do granular overlays. Because the design traffic is quite high, I did look at not importing anything and just reusing what we had and in situ stabilizing 300, and then you just had that 100 mil of sort of underlying crushed rock. That model didn't quite work in Circly. Yeah. So one of the most important things, while structural rehabilitation, has been discussed, is actually drainage itself, keeping water out of the pavement. And one of the best ways to do that is to obviously, crossfall, table drains, subsoil drains, sealing the cracks as they appear, flushing out the drains, making sure they're clean, making sure they're graded, making sure water always flows away from the pavement. We don't want any ponding on the road, near the road, anything like that. I do understand that sometimes we're constrained by the site topography, and that's always a concern, but wherever possible, we should grade the subsoil drains, grade the table drains, deepen the table drains, clean out the subsoil drains, flush them out, construct adequate crossfall of the pavement, of the sublayers where possible, and just keep the moisture out, keep the water out. Just for this presentation, the references were Ostroads Part 5 2011, Ostroads Part 5 2019, Ostroads Part 2 2012, and Ostroads Part 2 2017. Thank you for attending the presentation.